Please welcome a program manager from DARPA's Information Innovation Office, Dr. Sandeep Neema.
Good morning. Pretty exciting day and a half. By now, you've seen many exciting applications of AI. And I'd like to think that autonomous systems and autonomy is the most exciting application of AI. But it comes with a host of challenges regarding assurance. OK. So let me start with a few observations. Mission scenarios, like you see in this graphic, where humans are collaborating with autonomous systems, are increasingly envisioned by military planners. But to enable these kind of scenarios, the autonomous system has to perform many complex tasks. It has to make sense of a highly dynamic, complex, and unstructured environment. It has to detect and avoid static and dynamic obstacles. It has to interact with the human, understand their intent, and react to it. And ideally, through all this, learn the tactics and maneuvers and get better over time. Clearly, quite a difficult challenge. Now, the capabilities essential to perform these tasks, such as situation understanding, perception, behavior learning, planning and decision-making, all of these now employ learning techniques in some form or the other. So this is to say that learning technologies and learning systems will be essential to achieve autonomy in real world. But these are cyber-physical systems. They operate in a physical world, and safety matters. Incidents like the Uber crash in 2018 and the Tesla in 2016 have been highly reported and serves to underscore the importance of safety in this context. Errors in design, bugs in implementation, and now deficiency in training could result in fatal consequences. So the challenge is, how can we assure that these learning systems are safe and correct? Now, to appreciate the challenges in assuring learning-enabled systems, it's instructive to look at it from the perspective of what we know already in terms of non-learning system. The figure on the left of your screen is a conceptual representation of the state space of a non-learning system composed with its environment. And it shows the unsafe and safe regions of the state space. Now, the goal of the safety assurance in these cases is to prove that all trajectories of the system, starting from some initial state and under all possible actions of the environment, continue to stay within this green region and do not intersect and land up into the unsafe red region. Now, there is a long history of work in this space, and there are tools and methods that allow us to prove and demonstrate this. But when we come to learning-enabled system, even something as basic and fundamental as reachability becomes quite convoluted rapidly. And that is the case because learning-enabled systems include components whose behavior is not explicitly programmed, but is emerging as a process of training. And the manifest behavior is a complex interplay of interaction between the training data and the operational data. Learning, in this case, expands the reachable portion of the state space in ways that is difficult to characterize. So that brings up several challenges. How can we characterize the behavior of such systems? How can we ensure that these systems do not land up in the unsafe region? How can we provide some bounds on the behavior of these systems? So these are the class of challenges that we're looking in the context of this program. Now, traditionally, V&V has been thought of as a design time activity, something that's done prior to the development, prior to the deployment of the system. But for these class of systems, it is no longer the case that we can do all verification activity upfront prior to deployment, especially because the learning algorithms itself inevitably will evolve either through episodic learning in an offline sense or even online in some cases. So any approach to safety and VNV has to span both design time and operation time. So in the program, we are pursuing a collection of techniques that span both design time and operation time and cover these key categories, if you will. We're looking at modeling and specification approaches. We're building some new techniques for verification. For operation time, we're looking at approaches that can monitor and observe the behavior of the learning-enabled systems. We're looking at incorporating safety constraints inherently into the learning process. And we're looking at assurance cases and assurance measures. Now, I won't be able to talk through all of these, but what I'll do is give you representative examples from each of these areas in the next few charts. But before I talk about the approaches, let me make an argument that simulation alone is not sufficient for these kinds of systems, autonomous systems in general, but learning-enabled systems more particularly. Through this somewhat contrived but fairly realistic example. So the system in this case is doing waypoint navigation using neural networks. There's a planning component that generates waypoints and does the trajectory planning. And there's a neural network-based controller that's tracking these waypoints provided by the planner. And it's trying to generate steering commands based on the current state of that system and driving it towards the waypoint. Now, the typical approach for something like this would be to test it through a simulation, where you set up a simulation environment that includes the world and the environment, and the planner and the neural network is outside an actual implementation. And you can test it and simulate it through many possible variations of the scenario. And you can try this for a long time, and you may never get into a combination of conditions where the system might fail. But if you turn this around a little bit and ask the question differently by providing a precise query, abstracting the implementation to some extent, and posing a formal verification problem, then you'll quickly find out that indeed there is a combination of states and the position of the waypoint, in which case the neural network wants to steer in a direction opposite from where the planner wants the vehicle to go. Clearly not a happy consequence. So now that I've established motivation for verification, I'm going to give you a few examples of verification techniques that are working in this program and the context in which those techniques are applicable. The figure on the left here comes from FAA's Airborne Collision Avoidance System, or ACAS-X. The goal of this system is to generate advisories for the aircraft to either maintain its course or take turning maneuvers in case there is another aircraft in the nearby airspace. And it does so by taking these inputs, such as the distance from the other aircraft, your own position, velocity, and so on and so forth. The default implementation to this system uses a high-dimensional lookup table, which discretizes the entire state space, input space, and for each point in the input space, assigns a score to the advisory. Now, such an implementation ends up being too large and difficult even to accommodate in the memory of the system. And as an alternate, FAA is exploring neural network-based approaches to approximate this high-dimensional lookup table. A clever idea, but clearly begs the question, how can we assure that the neural network will generate the correct advisories given a particular set of inputs? And it's for these kind of queries, this particular verification approach is delivered to address. And in this tool, what they're doing is they take the description of the neural network and the property that has to be proven and map it into a system of constraints. And they solve these system of constraints using state-of-art SMT solvers. Now, the SMT solvers generally work well. They're highly scalable and efficient. But in these kinds of contexts, the challenge comes from the non-linearity of the activation functions that are part of the neural network. In this particular case, we are using ReLUs, or rectified linear units, which makes this problem difficult to solve. This work has been done by Professor Clark Barrett of Stanford University, And they built a tool called ReluPlex, which to some extent predates my program. But in my program, they're extending that work to cover other kinds of activation functions and more complex neural networks. So this approach and tool is effective in context of input-output verification problem. But a more typical usage where neural network is part of a larger system, and the property that we want to verify is a more system-level property. The example here in this case is an emergency braking system, which includes a camera sensor, a neural network that takes images coming from the camera, and generates inputs for the braking controller to stop the vehicle if it detects an obstacle ahead. The safety property that we care about in this context is that we want to make sure that the distance between ourselves and the vehicle ahead is greater than some safety threshold. Now, the SMT-based approach that I presented earlier does not apply in these kind of contexts because the space of input is coming from a very high-dimensional space of images. And even with symbolic methods such as the SMT-based approach, cannot exhaustively explore that space. So how do we do this? Well, by decomposing the problem into subproblem and providing some clever ideas around those. The first idea is to narrow down the context of the search and exploration, and posing this as purely a CPS problem by extracting away the machine learning component. The narrowing is in the form that you first look at regions of the state space where, regardless of the output of the machine learning component, where the property is always satisfied and we are always safe. So the green region, for example. Here, since we are slow and the obstacle ahead is pretty far, irrespective of what the neural network says, we're always safe. The red region, on the other hand, where we're too fast and the obstacle ahead is pretty close, we're already too late and the property has been violated, and regardless of the output from the neural network, we will run into collision. But the interesting region that we want to explore is this narrow region called the region of uncertainty. And this is the region where the correctness of the neural network matters. This is if the neural network misclassifies the object, then we'll end up in a collision. So that sets up a region for exploration. But here again, we cannot explore this region at a pixel-by-pixel level modification. So here again, we abstract the space into a much more semantically meaningful abstractions. I'm just showing 3 dimensions here. These are lateral distance from the car head, longitudinal distance from the car head, and brightness. Now, this is a much more manageable space that we can explore. And by sampling the space and using a generative approach, we synthesize a set of images that we test the neural network with. The result of this exploration are shown on the chart on the right. For most cases, the neural network performs correctly and recognizes the object and classifies it correctly. And these are the green circles. For several of the cases, the network misclassifies, and these are the red region on the top and the left. But most of this red misclassification end up being benign because either the car ahead is too far, or in some cases shown here, the brightness of the scene is artificially too high, not a realistic concern. But what's concerning are some of these reds, one or few, which are spread between this sea of green. These are real hazard. These are true corner cases, which is where, if not mitigated, we can get a misclassification and we'll end up in a safety hazard. This particular example, the network is not recognizing correctly, perhaps, because the car is too far to the left, and possibly a case which is not included in the training data set. So this work is done by Professor Sanjit Seshia of UC Berkeley, and they've built upon this baseline and implemented a counterexample guided data augmentation loop that takes counterexamples like this and augments the training data set and refines it through this counterexample augmentation process. So I started by telling that simulation alone is not enough, but simulation complemented with other approaches is an important component in overall assurance toolkit, particularly if you can buy down the cost of constructing simulation, concrete scenarios for the simulation. So in this approach, we are pairing up classical simulators, 3D world simulators, and pairing them up with probabilistic programming-based approaches, the kind that you saw in the talk yesterday. The probabilistic programming approach allows us to define scenarios as probability distribution over configuration of physical objects. The specific language is called scenic, and that allows us to define concrete scenarios in a generic probabilistic manner. In this particular example, we're interested in testing the ability of an autonomous vehicle to safely navigate around obstacles marked with traffic cones. So we specify the scenario by identifying the safety obstacle and the traffic cones around it as a set of constrained random variables, and then we sample from this space. And through the sampling, we find many concrete instances, and we try to steer the system towards scenarios which are safety constrained and which results in a crash or a violation. This work also comes from Professor Sanjit Sesha at UC Berkeley as an important component of our assurance toolkit. So let me switch gear and talk about runtime techniques for a little while. Now, when we use neural networks in safety-critical context, it's not sufficient to simply get a classification output or a regression estimate from the neural network. You also need to get a prediction uncertainty, a confidence measure that allows you to incorporate those in decision-making. And it's generally known that while accuracy of neural network is improving, their confidence estimation is particularly bad, especially if you recall seeing examples like where Panda and Gibbon, and the Gibbon is a misclassification, but there's higher confidence in that misclassification. So in this approach, we're building techniques to calibrate and provide confidence estimates over neural networks. The specific approach is based on ideas in conformal prediction, and that looks at a particular data set and how conforming it is with respect to the training data set, and how much support you have for this particular instance from your training data set. I'm not going to go into the algorithm itself, but let me explain this approach through this example, or the results of from this example. The context here is that we are using a neural network to maintain a track on a race course. The neural network is a simple feed-forwarded network that's generating steering outputs for the system. And the goal of the neural network is to minimize that track position error and keep the track position within this -1 to 1 limited yellow blue band region. Now, for the purpose of experiment and validation of the assurance measure, they've degraded the track towards the end of the simulation run, such that that portion of the track does not look similar to the rest of the track. And as you can expect, the neural network that's trained with the rest of the track does not perform very well towards the end of this. And you can see that manifesting in the high track error towards the end of that trajectory. In an empirical validation of sorts, the assurance measure that's shown in the blue line here seems to correlate well with the track, or correlate negatively with the track error. So where the assurance measure is low, the track error is high. This work comes from Professor Xenophon Katsoukas of Vanderbilt. And in current work, they're refining this assurance measure and looking at scaling up the implementation of this approach. Now let me talk about reinforcement learning for a short while. RL-based control techniques are increasingly popular in robotic research. There are many reasons for that, but the most prominent ones is that RL-based approaches, as opposed to classical control approach, do not require highly precise models of the dynamics of the system and its environment. An RL-based controller learns a control policy by exploring the control action space and reinforces the control choices based on the rewards. But in such an exploration-based approach, how can we assure that the system does not end up in some safety constraint violation? And so one challenge here is to incorporate safety constraints in the exploration process. The other challenge is that you may train the RL control and learn the policies over one environment, but when that environment changes, how can you ensure that we are still safe? So the example shown here addresses both of these issues in the following manner. The scenario here is there's a drone that's designed to track a particular trajectory and has to simply go up and down in this room. The floor and the ceiling represents the constraints in this case. And normally, it's trained through the RL controller. It learns to track this trajectory and starts doing pretty well. But the interesting variation in this scenario happens when the fan turns on. The fan, in this case, represents a step change in the environment. And of the two drones, one of the ones that's been equipped with the ability to detect this environment shift and react to it ends up flying safely, whereas the other one starts bouncing back and forth to the floor. Now, of course, when it does that, it's degrading its performance by not tracking the trajectory as close as you want it to towards the floor and the ceiling, but it does so in the benefit of the safety objective. OK, so just to summarize and wrap up, I want to reemphasize that learning technologies are important to achieve higher levels of autonomy in these class of systems, but safety is going to be critical and essential. In the program, we're building foundational techniques for assurance of learning-enabled systems, and I provided you several examples of what these techniques are. We're working with several industry and DoD partners to test and evaluate these technologies. Boeing is building experimental aircraft and equipping those with autonomy for us and building several challenge problems that span autonomous air and ground operations. Northrop Grumman is creating challenge problems that involve underwater navigation and surveillance types of operations. And TARDEC is building challenge problems that involve navigation in unstructured terrains. With that, let me thank you and answer any questions. So the question here is, how does the assurance work being done in this program relate to the self-driving industry? Do you plan to work with any of the commercial driverless car companies? So I'm going to say that the work that we're doing does have close bearing with the work that's being done in self-driving industry as well. Though we're not focused or limited to the driving scenarios alone, we are in fact looking at a broad spectrum of scenarios which involve use of learning technologies in context of cyber-physical systems. And so most of our scenarios span different domains relevant to DoD. We are not directly working with commercial car companies yet, but we have had interactions with some of the car companies by inviting them to our PI meetings and discussing some of the problems. Some of the performers in the program are building these tools and applying it to some of the car driving examples. For example, the probabilistic programming approach that I've described here is being applied and tested to some of the work with Toyota and so on. A second question here is asking, will the program address assurance through cyber attacks on LECs? So cyber attacks are certainly of concern to many research programs at DARPA and in I2O, and we're looking at it from multiple perspectives. Cyber attacks in a general sense applied towards autonomous cyber-physical systems, those are addressed through programs like HACMs and RADIX and so on. Cyber attacks directed specifically towards some of the machine learning techniques. I think you just heard Hava Siegelman talk about her work. And we're looking at assurance or resilience to cyber attacks to machine learning components, specifically in those programs. In my program, I'm not specifically looking at those issues, though some of the robustness approaches that we look at try to address challenges where delta perturbations in the input should not cause the machine learning system to misclassify or misrecognize the object in question. The other question here is, could the computational requirements for runtime assurance be so large that real-time assessment may be hard? So yes, some of the methods that we have, full-scale verification approaches, that can be very difficult to directly apply at runtime. But what we're doing is, well, some of the techniques we are optimizing, and others we're using abstraction-based approaches that allows us to scalably test these ideas in context of runtime as well. That's, I think, all the questions that I had. Let me thank everyone, and I should be available outside as well if there are additional questions throughout the day. Thank you.